Imagine a world where crabs are not just scuttling around the sand, but are part of a complex puzzle waiting to be solved. What if I told you that understanding the moment can unlock the secrets of graph theory? Alright, today we are diving into an intriguing challenge that combines creativity and logic as we unravel the mysteries behind crab graphs. Are you ready to join the adventure? Alright, let's dive into the heart of our crab graphs problem. We are dealing with a classic flow network scenario, and understanding how we structure our approach is crucial. So grab a seat and let's walk through the logic step by step. First thing first, we need to set up our environment. We declare a few constants and arrays. Max nodes defines the maximum number of nodes we can have in our graph. Think of it as setting the stage of our actors. Our nodes in this case, we have a 2D array called capacity. This will hold the capacities of our edges and an adjacency list ADJ to keep track of which nodes are connected. Now let's talk about the main challenge we are tackling, finding the maximum flow from a source node to a sink node. To do this, we employ a method called BFS or breadth first search. This is where we start exploring our graph. When we call BFS, we begin by resetting our parent array. This array is crucial because it helps us track the path we take through the graph. We initialize it with -1, indicating that no nodes have been visited except for our source node, which we marked as visited by assigning it a special value -2. Next, we set up our queue. This queue will help us manage which node we are exploring. We start by enqueuing our source node along with an infinite flow value. This is our starting point, and it's where the journey begins. As we delve deeper into the BFS, we dequeue our node and explore its neighbors. For each neighbor, we check two things: if it hasn't been visited yet, and if there is a capacity remaining in the edge connecting them. If both conditions are met, we mark their neighbor. We mark this neighbor with the connect with the current node and its parent. This is how we build our path. Just like where it gets interesting. If we reach our sink node, we return the flow, and that can be pushed through this path. If we exit the BFS without finding the sink, we return a flow of 0, indicating that there is no more capacity to push through. Now let's transition to the max flow function. This is where the magic happens. We keep running our BFS until it returns a flow of 0, which tells us there are no more paths left with capacity. Each time we find a new flow, we add it to the total flow. After finding a valid flow, we backtrack with using our parent array. This is like retracing our steps in a maze. We adjust the capacities along the path we just found, reducing the capacity for the future edges and increasing it for the reverse edges. This is crucial because it allows us to consider the possibility of pushing flow back in future iterations. Now that we understand how the maximum flow, let's look at how we build our graph. We begin by reading the number of test cases. For each test case, we reset our capacity and adjacency list, preparing for a new graph. We define our source and sink nodes. The source node is where our flow starts, and sink is where it ends. We then read in the edge connecting the head and feet of the crabs. Each connection indicates that a foot can be matched to a head, and we set the respective capacities. To set up the connections from the source to the head, we connect the source to each head with a capacity equal to the maximum number of feet each head can handle. Likewise, we connect each foot to the sink, establishing a capacity of 1, indicating that each foot can only be used once. Finally, we call the max flow function with our source and sink, and we print the result, which gives us the maximum number of feet that can be matched to heads. Alright friends, let's quickly recap what we have just learned about solving the graph problem. We dove into the code where we implemented a flow network using the BFS algorithm to find the maximum flow from a source node to a sink node. Key points included initializing our adjacency list and capacity matrix, building the graph based on input edges, and running the max flow function that utilizes BFS to calculate the flow while dynamically updating capacities. It's a classic example of how to tackle graph theory problems using the practical coding techniques in C#. So what's the main takeaway here? Understanding how to represent and manipulate graph is crucial in many algorithmic challenges. We saw how to efficiently manage capacities and track paths using the parent array, which can be applied to various graph related problems. If you have found this video helpful, don't forget to hit the like button and subscribe for more coding challenges. And stick around because in our next video we are going to delve deeper into more complex advanced algorithm problem, including Elmon-Scarf algorithms and how to optimize network flows even further. So you don't want to miss it. Keep the notifications on. Happy coding, and I'll see you in the next time.